I am honored to chair the first session of the invited lectures in geometry. On behalf of the Brazilian Mathematical Society and the entire Brazilian mathematical community, before we start, I would like to pay a small tribute to Manfredo do Carmo. Professor Manfredo, as we know him, is the father of differential geometry in Brazil and founder of a school of strong traditions in our country. His scientific contributions, especially in the area of minimal surfaces, are recognized worldwide for their depth and originality. He authored a very expressive number of research articles, as well as several textbooks that became standard reference in graduate and undergraduate courses in Brazil and abroad. Professor Manfredo passed away earlier this year at the age of 90, here in Rio de Janeiro. Nevertheless, Professor Manfredo is not to be considered a mathematician of the past, as his strong legacy survives through his students and scholars who will carry on his vision in the realm of differential geometry. I am now pleased to introduce the first talk. It's about Hodge theory and cycle theory of locally symmetric spaces from the University Pierre and Marie Curie, Mathematical Institute of Jussieu. Please welcome Nicolas Bergeron.
Thank you for the invitation. I will start. So the main character of this talk will be a discrete subgroup of Lie group and mostly arithmetic groups that were already mentioned several times yesterday, and their cohomology. And I want to start with some motivation and definition motivation, and to promote some heuristic about their cohomology. So the discrete subgroup I will be mostly interested in are lattices in a semi-simple Lie group. So if you I don't want to define what is a semi-simple Lie group. You can just take your favorite example between these groups, SL and R, SP2 and R as symplectic group, or an orthogonal group of a signature PQ, or a unitary group of signature AB, and take a lattice in it. So a lattice is a small subgroup in the sense that it's discrete in the natural topology, in the Hausdorff topology in the Lie group, but it is as well big as if you take the quotient and push forward the natural invariant measure on the Lie group, then the quotient has a finite volume. So that's the main object I want to study, and I want to study their cohomology. And the whole talk will be centered around promoting a vague philosophy, a vague general philosophy that in some sense that I don't know how to define properly, and I'm not claiming there is a real theory behind it, but it's rather some philosophy that will drive the different results I will mention, and hopefully drive further ratios in the future, is that the cohomology groups of this gamma, of these lattices, in many ways behaves like cohomology groups of complex projective manifolds. And so I want I will give some details about the general philosophy, but it's very vague, and in many cases I will restrict my attention to special classes of lattices, namely arithmetic groups. So let me say quite informally what is an arithmetic group. I don't want to give a precise definition. So you can just think as an arithmetic group as an integral point of a classical group. So take the same classical group as above and think of them as defined over the rationals, like SLN or SPN, and the z point is SLN z, SP2 and z. A deep theorem of Borel and Harishchandra says that these groups are lattices in the ambient Lie group. And as you can see on the slide, I also authorize the latter group, which is SL2 of Zi. So you may wonder why it's the Z point of a classical group. It rather look different, but it can be presented also as a Z point of a group. You just to consider a group of matrices, of 4x4 matrices in the way it's written on the slide. And then it really becomes the Z point of a classical group. And in the same way, you could consider integral point of algebraic group defined over a number field. But and you will still have arithmetic groups. Also, I will consider finite index subgroup of this arithmetic lattices. Mainly those given by congruence relation, and then I will just say that it's a congruent subgroup. But, so you can just think of them as special finite index subgroup given by congruence relation. For example, ask that the matrix is congruent to the identity modulo some big integer. Okay, so usually when I mention, and I'm not sure I'm the only one, but when I mention arithmetic group, the whole audience falls asleep or start opening laptops. So, arithmetic groups, yeah? So why should you keep listening? So it was mentioned several times yesterday, so hopefully you have some motivation. If it's not enough, then first, you might be interested if you're here by non-positively curved space and geometric group theory. And you may want to have a lot of examples in mind. And in fact, if you try to build up manifold, let's say negatively curved manifold of higher dimension, then think of it and it will be hard to build examples. And in fact, most of the examples, if you take their fundamental group, you will find arithmetic groups or combinations of arithmetic groups. So it provides a lot of interesting examples. If you are more complex algebraic geometer, then many nice examples in the complex algebraic geometry, let's say ball quotients, have fundamental groups that are lattices in Lie group. In that case, it's lattices in PU and 1. But also, if you are interested in many moduli problems, like moduli of abelian varieties, moduli of K3 surfaces, then the spaces have fundamental groups that are lattices and often arithmetic lattices, and especially if you are interested in Shimoda varieties, that's always the case. And finally, if you are interested in number theory, I hope you were convinced yesterday that you need to study cohomology of arithmetic groups. And maybe the reason why is that the natural generalization, so modular forms represent classes of cohomology in congruent subgroup of SL2Z. And the natural generalization, in some sense, the only generalization I can think of modular forms in higher dimension are cohomology classes of congruent subgroup in other group, let's say in congruent subgroup of SL and Z. So that's hopefully enough for the motivation. So please stay awake. It's only the first talk of the session, so I count on that. And now let's go back to the group, to a general lattice gamma. Associated to such a lattice gamma, there is a canonical space, which is not interested topologically. It's a contractible space on which gamma acts properly and discontinuously. But the space is a Riemannian, complete Riemannian space, which is called the symmetric space. And so when I say it's canonically associated, I'm a bit cheating here. The metric is only well-defined up to scaling. But apart from that, it's canonically associated to the lattice. And then you can form the quotient by the lattice, S mod gamma, and I denote it by X gamma. it's not necessarily a compact space, but it's always of finite volume. And I want to think of the volume of this space as a measure of the complexity of the lattice. Okay, so let's recall some famous example of that. The most famous is when you take a discrete subgroup of PSL2R that were called function group by Poincaré. Then this subgroup, to this subgroup is associated the symmetric space S, which is the Poincaré upper half plane. And the action by gamma on this symmetric space is the usual action by fractional linear transformation. And it preserves the standard hyperbolic metric, the Poincaré metric, written on the slide. And the quotient, S mod gamma, is a Riemann surface. But in this talk, so this is a very special example where the symmetric space S carries a complex structure. But in this talk, I rather want to deal with any symmetric space. And in general, these are not complex manifolds. So I will forget about the complex structure and rather insist on the hyperbolic metric. And to take another example, another very important and classical example, take a discrete subgroup of PSL2C, such that PSL2 of Zi in the first slide. Then these are called Kleinian group by Poincaré. The associated symmetric space is a three-dimensional hyperbolic space. So it's a real manifold of dimension 3. And of course, it carries no complex structure. And the quotient is a finite volume hyperbolic 3 manifold. In many cases, you can just think that the quotient is compact. It's not very important for my talk. And so, as I said, I will be interested in the cohomology of these lattices gamma. If you don't know if you're not familiar with group cohomology, you can just take the cohomology of the quotient x gamma. The general philosophy I want to promote is that these groups, also x gamma is in general not a complex manifold. This group behaves in many ways like cohomology group of complex projective manifolds. And to start with, I want to say that there is a natural Hodge theory for these spaces. This natural Hodge theory goes back at least to Matsushima, and the algebra of this behind this Hodge theory has been fully understood by Vaughan and Zuckerman. So these are Matsushima, Vaughan, and Zuckerman. And the way I will present it is essentially due to a presentation by Akshay Venkatesh. So first, let me recall briefly what is classical Hodge theory. So if you have a compact Riemannian manifold, then the cohomology class can be represented by a differential form, thanks to the Ram theorem. And because you have a Riemannian metric on M, you can pick a particular representative of a cohomology class. It can be represented by the unique differential form, which is of minimal L2 norm on the manifold. So there is a better representative thanks to the Riemannian metric, which gives a norm on the differential form. And the differential form, which is of minimal L2 norm, is an harmonic K form. And so you identify the cohomology of the space with the harmonic forms. So that holds on any compact Riemannian manifold. But now, if the manifold happens to be complex, then there is also an action of the circle on the space of differential form. And this action of the circle, if you assume moreover that M is a Keller manifold, which is the case of complex projective manifold, then this circle action preserves harmonic form. So you have an action of the circle on the cohomology. And if you decompose this action of the circle into isotypical components, then you get the Hodge theory. You get the decomposition of the cohomology. So let me say it in slightly differently. So from a Riemannian point of view, Keller means that the metric has a restricted holonomy. it has smaller holonomy than the generic manifold. The complex structure on the tangent space is preserved by parallel transport. And in fact, there is something very similar for locally symmetric spaces. They also have, in general, a highly restricted holonomy. And this gives algebraic structure that are algebraic structure on the tangent spaces that are invariant by parallel transport. And this gives, in turn, extra algebraic structure on the cohomology. So, in brief, what you get in doing that is Hodge theory for the quotient x gamma, which provides a canonical decomposition or canonical splitting of the cohomology of gamma. In this decomposition, you first see the first part, the most trivial part, which is the invariant part of the cohomology, represented by harmonic forms that are invariant under the parallel transport. And then you have a filtration by forms that are less and less invariant, that looks very much like the Hodge decomposition for Keller manifold. I won't describe the full algebra, it's rather intricate. It is a theory of GK cohomology. But I will take an example considered, as I said, by Venkatesh in his Takagi lecture. And very, very nice and simple example. You take, let's say, a product of 3 copies of the hyperbolic tree space. So the corresponding Lie group is a product of 3 copies of PSL2C. And you take some lattice inside this product. I will also assume that later that the lattice is irreducible. And it means that the quotient cannot split do not split as a product. Then, very analogously to what happens with scalar manifold, the harmonic form on the quotient x gamma splits as 3 types of harmonic form on each factor. And so this decomposes the cohomology into subspace HABC, depending on the type of form you have on each of the factor. And then you can group terms, and the invariant part of the cohomology corresponds to forms that are of type 0 and 3, 0 or 3 on each of the factor, and the other part of the Hodge decomposition is the rest. And as you see, because gamma is irreducible, here there are some HABC that are missing, for example, H100. And the conclusion of that is that there is some kind of analog of the Hodge diamond. The decomposition puts much structure on the possible vectors of Betti numbers. Apart from the usual Poincare duality constraint on the Betti numbers, here the vector of Betti numbers has to be of a very constrained form that I have written here. So that's a general phenomena. It holds for any locally symmetric space. The Hodge decomposition gives constraint on the possible Betti numbers. And so the next question I want to address is apart from this constraint, what can be the Betti numbers? I will only address a very general question, the growth of Betti numbers. So if you want to forget about Hodge decomposition, you can forget for the moment. We change slightly the subject. I will now consider how the Betti numbers behave. And here again, I will be guided by the analogy with with complex projective manifold. So as you see on the left of the slide, I consider a complex projective manifold. In fact, I consider a particular one. I take a hypersurface of degree D. You can think of D as measuring the complexity of this manifold. In fact, it's also essentially the volume for the natural volume form on the projective space. And it's not hard to prove that if you let the complexity tends to infinity, so if you let D tend to infinity, all the Betti numbers tends to be remain bounded, except in the middle degree, where there is really where the interesting new topological phenomena occurs. And in the middle degree, I recall that M is a hypersurface, so it's of complex dimension n. and therefore of real dimension 2n, so n is the middle degree, and the Betti numbers grows like a power of the degree, d to the n plus 1. And in fact, we have a slightly similar phenomena on the locally symmetric space side. So now take a locally symmetric space. The complexity, as I said, I want to measure it using the volume. So let's say a volume V. And what happened here is that away from the middle degree, the Betti numbers are not bounded. It's not true. They can be big, but at least they are sublinear in the volume. And here again, the only degree where it can be where there can be a big Betti numbers is the middle degree, and it grows linearly with V if the Euler characteristic. Okay, if this number, the Euler characteristic of the dual symmetric space, is non-zero. I don't want to define this, but let me just say that this is non-zero precisely when the defect delta mentioned by Peter Sarnak yesterday is equal to 0. So now, before some of you scream, I must say that this theorem is not, that's why I haven't put theorem, it's not completely true. It's not true, as I said. You have to make some hypotheses on the locally symmetric spaces. In general, it's false. But, so let me state a precise theorem that is the result of accumulation of works that started with De George Wallach that was mentioned by Sarnak yesterday. And the statement here you can prove in the recent paper that is often referred as the 7 samurai because there are too many authors to give the whole name. So here are the 7 samurais that contributed to the paper. Miklos Abert, here, Jan Bieringer, Tsarik Gelander, Nick Nikolov, Jean Rimbaud, and Ido Samet, and myself here, with a few years less. Tsarik will certainly mention part of this work more in his talk this afternoon. But for my purpose, I just want to say that if the group G has property T and rank bigger than 2, if you don't know what it means, take SLNR with n bigger than 3, or SP2NR with n bigger than 2, for example, then the growth of the Betti numbers of locally symmetric space are exactly what I said in the previous slide. So then the theorem is true. The problem is that in rank 1, the theorem is false, but quite recently, thanks to work of Rakshik and Rimbaud, it has been extended to the arbitrary case. You can take S arbitrary on the condition that you stick to congruence arithmetic manifold. So I told you sometimes I will stick only to congruence arithmetic manifold. Then if you stick to this case, then you have the growth mentioned in the theorem. So this is very analogous to what happened in the complex projective manifold. So now we have two things, an analog of the Hodge theory. We know that there is a rich topology, there can be rich Betti numbers. So the next thing that I want to do is to understand the cycle theory. So in general, homology wanted to capture how behaves submanifold, how they bound together, and so on. Now we have Betti numbers. How can we get back to geometry and represent this class by cycles? And that's what I want to call Archetype Theorem, because of course the main guide behind this is the Hodge conjecture for complex projective space. So let me briefly recall what is the Hodge conjecture. You take a complex projective manifold, M. When you have a cycle, when you have a closed analytic subspace, so I want to restrict cycles to the same category, so analytic subspace of M. If it is of complex codimension P, then in cohomology it represents a class of degree 2P, but it's a particular class. In the Hodge decomposition, it occurs it is of type PP. It cannot be anything. And another constraint is that, of course, because it's represented by a submanifold, it is a rational class. So if we if we first want to deal with linear algebra, we will retain that it is a class of type PP which is rational and name this a Hodge class. And the Hodge conjecture is whether any Hodge class is a rational combination of such cycle classes. You can, starting from that, you can ask a lot of similar questions. Maybe the most basic question would be, if you take a general manifold, a real manifold, and a rational homology class, is it a linear combination of submanifold? And this is true. This is a theorem of Thom. If you have a complex manifold, you want to restrict your cycles to be complex submanifold. If you have if you have a symmetric space, you want to restrict maybe to subsymmetric space and see how much of the topology you capture. So, in principle, what you do, you look at all the in the Hodge decomposition, where do subsymmetric space contribute, and then ask, in this subspace, if the intersected with a rational subspace, can it be spanned by locally subsymmetric spaces? So this gives a lot of questions. It's hard to that are in general hard to solve. Let me stick to maybe one of the simplest cases, the case of real hyperbolic manifolds. So take the real hyperbolic space Hn that I want to realize. I will to take the following model, the model of negative lines of Rn plus 1, negatives with respect to a fixed quadratic form that I will assume to be rational. So quadratic form Q of signature N1, and I take all negative lines. Once you have that, then you can have a lattice in the asymmetric group of the hyperbolic space. You just take the integral point of the group SOQ, of the orthogonal group of Q, or any congruent subgroup of this. And you end up with this, with a manifold M. And now the kind of theorem we want to prove, and we prove in that case jointly with Chi-Wan Lee, John Minson, and Colette Meuglin, is that at least when the degree of the cohomology is small enough, here smaller than n over 3, where n is a dimension, then the rational vector space, here, because it's hyperbolic space, the Hodge decomposition does not give you, does not refine is not a refined decomposition. It's, so you consider the whole rational cohomology. And the theorem says that the whole rational cohomology is spanned by totally geodesic subspace, so hyperbolic submanifold of a smaller dimension. And let me take an example to be more, a little bit more concrete. Take work in codimension 1, so R equal 1. Pick an integer n bigger than 3 because you want the theorem to apply. Now, any time you take a rational vector in Rn plus 1, you can consider the hyperplane. The hyperplane orthogonal to this vector. So all the lines in Hn that are orthogonal to V with respect to the quadratic form. So this is a hyperbolic space of dimension n minus 1 associated to the restriction of Q to the orthogonal of V. And this hyperplane projects onto M, and because the vector is rational, it projects onto a codimension 1 submanifold of finite volume in M. And the theorem says that if you consider Poincaré dual of these cycles, this gives class in H1 of MQ, in fact, they span the whole cohomology. Okay? So that's the theorem. And of course, so it has a Hodge type flavor, but it does not use at all complex geometry because there is no complex geometry here. However, the same tools apply to other symmetric spaces that have complex geometry. So the nice thing here is that you go back to the original Hodge conjecture by applying these tools to, let's say, Ball quotients. So in particular, they apply to Ball quotient, arithmetic Ball quotient, or in other words, Shimura variety uniformized by the complex ball. And then you can prove that any Hodge class of type RR with R sufficiently small, so a away from the middle degree. As I said, the middle degree will be always the richer case and the harder to understand. Then if you are sufficiently away from the middle degree, then the Hodge conjecture is true. Okay? So that's the type of result that one want to prove, guided by the Hodge theory, by the Hodge conjecture on complex projective space. And now I want to continue by to consider another type of result guided by complex projective space. But now the type of result comes from the hyperplane section theorem. So the hyperplane section theorem has guided a lot of work on locally symmetric spaces. It started with Oda and followed by with work of Harris, Janshuli, Venkataramana, and Clausel, joint work with Clausel. So first, let me recall briefly what is the hyperplane section theorem. You start again with a complex projective manifold. And inside the projective space, you take a hyperplane. And you choose your hyperplane to be transverse to the manifold. Then you can cut your manifold by this hyperplane, and you end up with a manifold of complex codimension 1. And the theorem tells you that the homology of the smaller manifold, in fact, captures essentially all the homology of the big manifold, except, again, in the middle degree. So to be precise, the natural map from the homology of the intersection between the hyperplane and M to the homology of M is an isomorphism in degree less than the half the dimension minus 2. And it's still surjective in degree complex dimension of M minus 1. So that's the kind of theorem that should be used as a guide for in the case of locally symmetric spaces. And in fact, I should mention that there is a homotopical analog of this theorem. You replace homology by homotopy group, and it's still isomorphism. You still have isomorphism or surjection in the same degree. So what can you do in the case of locally symmetric space now? Yeah, they don't embed in another space, so you cannot take a hyperplane section. But still, you have natural subspace in it. You have locally symmetric subspaces. So you want to replace hyperplane section by locally symmetric subspaces. But it's not hard to see that a locally symmetric subspace in general that will not visit enough the big manifold. It's like a geodesic in a hyperbolic surface. It will stay in a small part of the manifold, so you cannot expect to capture all the topology using only one locally symmetric subspace. This has been addressed and fixed by the authors I mentioned, and the idea is to consider arithmetic manifold and to use what is called Eke translation. So you translate your manifold, and if you translate all of them using Eke operators, then you may hope to generate the whole homology. There is a lot of result in that direction that mentioned in Venkatarama's ICM talk in 2010, especially, and there are some results, new results I mentioned in my written address. Here, I rather want to address the other part, the injectivity part. So in this part, in this first case, you were trying to generate the homology using Eke translate of subspace. Here, you are trying to show that the homology of the smaller subspace inject in the homology of the bigger subset. And let me mention one homotopical version of it that worked for hyperbolic manifold, and that was proved with Frederic Haglund and Danny Wise. So start with a closed arithmetic hyperbolic manifold, and take a codimension 1 totally geodesic submanifold. So a hyperbolic submanifold of codimension 1. Then, essentially, what the theorem says is that we have a retraction of the big manifold to the smaller manifold, except that it's not quite true. There is this virtually word here, and I will explain what it means now. So let me call the manifold Hn over gamma. So what will play the role of the hyperplane is the projection of a hyperplane in Hn to the quotient. So you take a hyperplane in the hyperbolic space, so it's a totally geodesic hyperplane, so it's sub-hyperbolic space of dimension n-1, and you suppose that the projection in the manifold, so H over the stabilizer of H in gamma, is compact. So it's like a geodesic inside a hyperbolic surface. Then, if you have that, it's not quite true that gamma surjects onto the stabilizer, that there is a retraction of gamma onto the stabilizer of H in gamma, but there exists a finite index subgroup gamma prime in gamma, and a morphism gamma prime toward the stabilizer of H in gamma prime, which is the identity when restricted to the stabilizer. So it's a retraction, but up to a finite cover. And so as I said, this is a homotopical version, but in particular, if you apply now homology, it implies that the homology groups of the smaller manifold inject in the homology group of the bigger manifold, but only once you've passed to a finite cover. It cannot be true without passing to a finite cover. It's the same problem that in general you have in a hyperbolic surface, you have a geodesic that is trivial in homology. But passing to a finite cover, it becomes injective. So as any math talk should contain a proof, I will try to say a few words on this. And when I say word, I will rather say movies. I should rather say movies. So I will consider a particular example of hyperbolic manifold and explain where does the retraction comes from. And so first, let me describe what will be the example of hyperbolic manifold. It starts with a right-angled dodecahedron. And when you start with a right-angled dodecahedron and make reflection in the faces, then you get a tessellation. So you have to imagine that all the right-angled dodecahedron have the same size here. And you make a tessellation, it becomes like a ball. And if you enter into this ball, you will see a tessellation of the hyperbolic tree space by right-angled dodecahedron. So around each edge, you have 4 dodecahedron. And so the group generated by the reflection in the face of the right-angled dodecahedron gives a lattice in the isometry group of H3, namely into PSL2C. So the group gamma I consider is a group generated by reflection in the faces of this dodecahedron. Okay? And now I want to consider a cycle in this, and the cycle will come just from a face supporting just from the hyperplane supporting a face of this dodecahedron. As you see in the movie, the set of elements in gamma that preserve the plane supporting a face is just the reflection into the edges of a right angle pentagon, which is a friction group. It acts co-compactly on the hyperplane here. Okay, so you have now 2 groups. You have gamma, which is a subgroup of PSL2C, which is generated by reflection into the face of the right-angled dodecahedron. And you have a subgroup of it, which is a stabilizer of this hyperplane, which is just the Coxeter group associated to a right-angled pentagon. And now you want to prove that, now we will see immediately that there is a natural retraction of gamma onto lambda. The reason is exactly because the dodecahedron is right angle. So now if you can think of each dodecahedron as an element of gamma, because you start here with the trivial element. When you take a reflection, you have a first element here. Reflection on this face, you have another element. So each dodecahedron in the big tessellation can be think of an element of gamma, and this is coherent with the group multiplication. And now what will be the retraction? each time you have an element of gamma, so it is a dodecahedron in the tessellation, then you can take its orthogonal projection onto the hyperplane. And its orthogonal projection is a pentagon, which you can think of an element of lambda. So the retraction is just the orthogonal projection. Okay? So because you started with a right angle, and it's very important it's right angle, because you started with a right angle dodecahedron, the projection onto a face gives a retraction of the full group gamma onto the stabilizer of the hyperplane. Okay? Now, can you click on the... Now the general proof is a bit involved because you have to go to higher dimensional right angle space, and you have to go beyond hyperbolic space, but the principle is exactly that. And I won't say no more about it. I just want to conclude with the last analogy between complex projective spaces and locally symmetric space, because up to now we have been very limited to study the cohomology away from the middle degree. In the middle degree, it's quite clear that the cycle theory will be more hard to understand. Subsymmetric space won't be enough to explain all the cohomology classes. You have to find other type of classes, and the geometry will certainly be complicated. So maybe we can propose something more modest. So as I said, the cycle theory of locally symmetric spaces become very mysterious near the middle degree. So instead of trying to pin down exactly what is a good cycle representing a homology class, we may just ask the following question. Try to bound the geometric complexity of cycles that are needed to generate homology. In some sense, when you take totally geodesic cycle, you cannot hope for a better cycle. The geometric complexity is very simple because it's totally geodesic. Here, what can you say in general? So a way to do that is to introduce to encode this into natural period matrices. And so it's not the same kind of period matrices that you see in the complex algebraic geometry, because here it's not complex algebraic geometry. You don't have complex structure, but still you have a Riemannian structure. So you have a preferred basis on the cohomology. You have the harmonic forms. And so what you can do is compare this basis of harmonic form with a geometric basis, with an integral basis of the homology. So you have the integral homology of the symmetric space. Take a bunch of elements that project to a basis of the free part. So that's the cycle part of the theory. And you have the metric part of the theory, which are the harmonic form on the locally symmetric space. And you want to confront this by computing periods. So you form the period matrix here. And now, remember that the complexity of gamma, the complexity of the manifold, I told you I wanted to measure it using the volume. Here, I will compute some kind of volume of this. You have this matrix. I will compute the determinant of this matrix. And this was introduced by Akshay Venkatesh and I, and we call it the degree G regulator of the locally symmetric space. So the degree is the degree of the cohomology or homology group we are considering. And we take this determinant. It does not depend on the choice of basis here. And now, let's look at what can we say about this determinant. If you consider top degree or degree 0, then it's very related to the complexity of the group. It's essentially given by the volume. So the degree 0 is 1 over square root of the volume, and degree n is square root of the volume. In general, it's much more hard. It's much harder. It's harder to compute these numbers. But Poincaré duality at least tells you that you always have that Rj times Rn minus j is equal to 1. And the conjecture that follows follows from a work with Akshay Venkatesh and Alok Sangun, is that if we fix the symmetric space and fix the degree, then, okay, one can ask how complicated is the size is this number? How big is this regulator? And maybe the most simple thing one can hope is that the logarithm of this regulator is small o of the volume. This seems not big, not a lot to ask, and I will say a few words on why to expect this. I even hope that we should ask that this regulator should be polynomial in the volume, but let's be cautious here. And I want to insist that here I put congruence arithmetic manifold. And we have good reason for that, because there is a very nice work of Brock and Dunfield, where in the case of tree manifold, so hyperbolic tree manifold, in non-arithmetic case, they construct a sequence of closed hyperbolic tree manifold of arbitrarily large volume, so the complexity tends to infinity. The first Betti number stays equal to 1, but to find cycles of degree, a surface that represents this Betti number, then you have to find a surface with very high complexity. It has to be of very high Euler characteristic in the sense that the log of this regulator R2 stays bigger than some uniform constant times the volume. So the conjecture above is false in general if you don't put congruence arithmetic. And in the 39 seconds I have left, I just want to say that we started to investigate this conjecture in the case of hyperbolic spaces and congruence subgroup. So for Bianchi group, especially for Bianchi manifold, it's quite hard to say something meaningful, but in some cases we have partial results that support this conjecture. And the interesting point of the proof is that it relates the complexity of these cycles in degree 2, which is really a topological or geometrical complexity, and that's related to some very algebraic quantity, which is the height of an elliptic curve that should be associated to this cohomology class. And this will be maybe addressed by Akshay in his plenary lecture in more general situation. Okay, I will stop here and with some pictures because math is done with many people, and all these are my co-authors. So Frederick Haglund I already mentioned. I want to insist on Joss Less with the great guy we made all the movies you've seen in this. I'm sure you already heard of him, but he made all the movies here. And Chi-Wan Lee, John Milson, Colette Meudlin, Alok Sangun, Akshay Venkatesh, and Danny Weiss. Thank you for your attention.
Okay, we have time for a few questions.
So this virtual retraction theorem, does it also hold for finite volume non-compact? The virtual retract theorem for hyperbolic manifolds onto code mention 1.
No. That's why I stated. Okay, we can discuss some cases with.
More questions?
Do you have some kind of notion of a Hodge structure for these quotients, which are not necessarily algebraic? Do you have any notion of a mixed Hodge structure even in some special cases? If you try to take the complement of a symmetric space quotient inside it?
No, not really. No. But there should be, but it's just that I'm too lazy. I mean, there are some work of Harris and Zucker which do some, it gives some mix of, but to my knowledge, I think it's only on not sure what is known about outside Chinois varieties.
Would anybody like to ask another question? Well, if not, let's thank the speaker again for this beautiful talk.